Hi everybody. Today I'm going to talk to you guys about projectile motion and energy in specific. So we haven't really defined projectiles yet, and we haven't really talked about energy in a little while, though we've been talking about motion for quite a while. We haven't really referred back to energy. So I want to do that at this point, just to kind of keep us on track for our exploration of the basic kinds of energy. So let's imagine for a moment the scenario for the discussion is that I have a rocket, and the rocket has been set up so that it has some angle with the horizontal. And so I'm going to go ahead and just kind of quick draw out this angle right here, and I'm going to say that's angle theta sub ln, which is going to stand for our launch velocity, or launch angle, excuse me. So that's our launch angle. Now the launch angle is not 90 degrees. If we were only talking about upward and downward motion like we did last unit, we'd be still in unit 2, and so we wouldn't really need to be going in to depth like we're doing right now. But oftentimes things are launched at angles, and so we want to try to explore that motion. Now, it's not just rockets that do this, right? Obviously, if you kick a soccer ball, or punt a football, or throw a football, or shoot a basketball, all of those are projectiles. All of those things are launched, and they're all launched at different angles. And you intuitively, you don't sit and calculate that before you do it. You actually intuitively put that together in your head, some subconscious place in your brain that tries to figure out what the correct launch angle would be and what the correct launch velocity would be, as we're going to talk about in a minute, which I think is pretty cool. Your brain can do that without you really thinking about it too much. Anyway, speaking of launch velocity, this whatever launch mechanism for us in a couple of weeks when we go out and do the rockets on the launch on the practice field for the football team in the back of the school, we're going to use air pressure to be able to do that. So we'll pump up the air inside the rocket until it hits a certain pressure, and then it will violently escape backwards, and that will cause the rocket to move forwards with some velocity. And so I'm going to draw that velocity over here. You know that it's actually acting on the rocket, but I want to draw this velocity over here, the launch velocity vector. So let's imagine it looks like this. That's not perfect, but it is what it is. So there it is, the launch velocity vector. Now, what's going to happen as it goes through the air is it's going to be affected by two things, right? So the first thing is air resistance. And so this air resistance idea really serves to complicate our math and to make things messy. And so I'm going to ask for you to do something for me, and that is something you probably will appreciate doing. That is to make your math easier. We're going to assume for a minute that it's ideal conditions. So we're going to get rid of our air resistance. Ideal conditions also gets rid of friction, but we're not really worried about it for this case. So anyway, the object is now flying through the air, and it's not being affected by air resistance. It is being affected, however, by the other important force, and that is gravity. So we define a projectile as anything that's moving under the influence of gravity only. So you may realize that for this rocket, and for a basketball that's shot into the air, and for a football that's punted, the initial force that's applied to it is actually quite quick, right? It starts and stops in a very brief period of time, and then the object is given this velocity. And then what happens then is the only thing that we have that's affecting it as it goes through its motion is the gravity changes. And the gravity changes, right, are changes in the velocity vector, and it's equivalent to the gravitational acceleration. So you guys remember that this little g, gravitational acceleration, is 9.81 meters per second. But notice I put that vector sign in there, so I want to just point out the fact that it's down. It's always acting downward, and it's always acting, so don't forget that. So I'm going to come over here, and I'm going to say that this motion, which starts off in that direction there, actually is being affected by gravitation. So there's this little gravitational acceleration that is trying to affect the motion, like so, as it goes through its whole path. A projectile's path is called a trajectory, and I think you'd agree that that's a parabolic trajectory. So just keep that in mind. That's what that word means. If I say it in reference to a projectile, you know what I'm talking about. I'm talking about the path that it follows. So this acceleration, all of these are actually little g, right? Little g, little g, little g, all over the place. Wouldn't you agree that little g is the same throughout the entire path? It doesn't change. It always affects the motion in the downward direction by the same amount, this 9.81 meters per second for every second that it's going through the air. And so this velocity changes in this downward way each second that it goes through the air. So let's say the first second, now it's after starting with this initial launch velocity here, now instead we have to add this little g to it. Right? So little g I drew like so. And so after 1 second, it's no longer doing that anymore. It's no longer doing this anymore. Now its velocity looks like this. And then after another second, we apply gravitation again. And so its new velocity will look like this. And then after another second, it will continue to go downward. And so you can see that this gravitational acceleration is the cause of the shape of this path. So you see how the velocity vector changes over time. It's going to get further and further down until finally you have basically the exact opposite of what it started out as. And so that's what you're ending up with as you go through this path. Right? Gravitational acceleration is causing the change in the velocity for every second that it moves through the air. So, do you notice, though, that the gravitational acceleration only acts downward? Is there anything that changes the horizontal component of this vector? So let me draw it out again here. I'm going to draw this launch velocity here again so you can see it. So it looks like this. That's the initial launch velocity vector. So you can, if you want to, go ahead and talk about just the horizontal component of that, or you could talk about just the vertical component of that force, or excuse me, of that velocity. Getting ahead of myself there. And which one of those two is being affected by gravity? I think you'd agree that because this is horizontal and this is vertical, and gravitational acceleration is vertical always, that only the gravitational acceleration is only affecting the vertical part of the velocity, the vertical component of the velocity. And that's why I had you learn the component method for vector addition, because it helps you to start thinking about vectors as horizontal and vertical components rather than the actual angled vector that it has. Okay, so last little piece here. I'm going to erase all this so I can draw in something else here real quick. And that is this. If I wanted to, there we go. If I wanted to, I could say that initially here, the rocket is given a huge amount of energy, and it's specifically energy of motion, or what we would call kinetic energy. Initially, because of whatever this force is, it's given a huge amount of kinetic energy. Okay, so I'm going to draw a little arrow here to say that it has a huge amount of that kinetic energy. As it gets higher and higher and higher, you might remember from Unit 2 that the kinetic energy slows down. In fact, what ends up happening is by the time it gets to the top of the path, the velocity is only in the horizontal direction. So this horizontal component right here is what we have only at the top of the path. Like that. So kinetic energy reaches its minimum when it's at the top of the path because it's only moving horizontally for that one brief instant it's at the top. Do you remember from last unit when we talked about the fact that the object thrown straight up will actually stop briefly, just for an instant at the top of its path, and then begin to move its way down? So we can't change the horizontal motion, but we can change the vertical motion. And so the top of the path has the smallest amount of motion because it's all horizontal at that one point. And then it begins to increase its speed in the negative direction again. And so we end up with a velocity vector that looks like exactly the opposite of the launch velocity. I tried to draw that as best I could there, right there, when we get down to this side over here. And so we have a large velocity vector here, and a large velocity vector here, and a small velocity vector right there, the smallest it can get in this path. And so here's what, here we go, whoops. So I think you'd agree that here we still have a very high amount of kinetic energy because the motion is just as big at the beginning as it is at the end. So where does the energy go? It starts off big and it ends big, and in the middle it's small. So where does that energy go? And the answer is that there's another form of energy that we haven't talked about yet, and that's called gravitational potential energy. And so at the top here, we have exchanged some of the kinetic energy for this new kind of energy, gravitational potential energy. And potential just means it's stored in the object to be used later for motion. That's at least one of the ways to think about it. So at this point, this gravitational potential energy, which we signify with a, for reasons we don't want to get into right now, capital U sub G. G means just gravitation, right? So capital U is is potential energy. So at the top here, I think you'd agree that the gravitational potential energy is what is taking up most of the energy that comes from the kinetic energy. So it started off high, it got low, and where did it go? It went into the gravitational potential energy. And then as it starts to come back down again, the gravitational potential energy goes back down. So initially we've got high kinetic energy and low gravitational potential energy. That kinetic energy becomes potential as it gets higher and higher and higher. And so at the top here, it has maximum potential energy and the lowest kinetic energy. And then as it begins to fall back down, it increases in its speed, so it gains kinetic energy, but then loses this gravitational potential energy. And so you can see right here that the sum of it is going to be constant as it goes through its path. It's just going to exchange back and forth between the two types. That works as long as we have ideal conditions. So hopefully that makes sense. So that's projectiles and energy. We're going to talk a lot more about gravitational potential energy and kinetic energy in the next few units. So hopefully that helps. If you have any questions, please let me know. Thanks for watching.